Please welcome Manuel Yoon, VP of Strategy of Autobrains.
Thank you. Thanks. Hello, everyone. Maybe first of all, who is Autobrains? Autobrains is an Israeli software startup in the AI space. So my talk will also be a bit more about AI than software. And I would say we operate in the most exciting space in terms of software that you can operate in, which is the ADAS and AD tech space. We are about 150 people, and we completed last year our Series C funding in terms of $120 million, backed by Continental, Knorr-Bremse, BMW Ventures, and also Temasek, a big Singaporean fund. So that makes us, this is important in these times, one of the most well-funded startups in this space. And we are actually a spin-off of a bigger company that was founded in 2007 that aims at mimicking the learning process of humans. And this company is called Cortica and exists since 2007. And this is where the core technology was developed, and we are a spin-off, only focusing on the automotive space since 2019. And I think this is the most exciting space because there is one player in this segment that has a dominant market share of, I would say, 60 to 70%. And in my 10 years before in my previous job, I find it hard to find any other segment in the automotive space where one supplier has 60 to 70% market share. I don't know if you know any segment maybe that you've worked in automotive. I would be happy to hear about it, but I don't know any other segment. And this is good because this means there's also opportunity for disruption, and the industry is looking for alternatives. And this is why we try to use a different approach when it comes to ADAS and AD with AI. And this is to reverse engineer how the human perception works. This number is maybe one number that you can take with you from this day, and this is the amount of money that has flown into development of AV tech between 2010 and 2020 as an estimate. So number today is even higher, and this money was spent on semiconductors, sensors, software development, and so on. It's what the industry has spent, more than $100 billion. And today we are here. Yeah. This is where we are. And even someone like Anthony Lewandowski, who is a co-founder of Waymo, said you will be hard-pressed to find any other industry that has spent so much money in R&D, but has actually so little to offer and to show. And of course, now since last week, there's even more news on a player like Cruise because there were some fatal accidents. And the California DMV has actually suspended the license effective immediately. And there were other incidents and so on. And the response from the Cruise team was that they have a team of experts analyzing how their system can have prevented these very rare cases that the vehicles came into. And I think that the $100 billion or more north of that on the one hand side, and such images, and then there are other crazy images, of course, and videos that you can find on the internet, not only from Cruise, but also from other players. They show us where we are today, and that maybe we need to fundamentally rethink the approach that we're taking to solving autonomous driving and ADAS tasks. And I'm just talking about this from an AI perspective, where there are three main gaps. The first two ones, I think there were some strong examples that we know of or that we see, which is first the cost, not only in the R&D side, but also in, of course, the components and in the software development, and how to cover these edge cases. So we face still the long tail problem, and the way that the industry is approaching this today is to say more is more and more and more and more. So for example, Tesla, they are building now for $1 billion this year, and I think $2 billion next year, a 100 exaflop compute cluster. You have players like Mobileye that have 200 petabytes of data. And the question is really, is this the right AI approach that we are using to tackle this problem? And third, you still have the gap between perception and decision making. So that's something that's, from an AI perspective today, not jointly solved all of the time. And this creates also problems, so it's another challenge. So I just want to, let's say, critically ask and use the forum, is this really the right approach that we are taking? Because if you ask the companies today, they will say, yes, we are not only software first, but we also do AI first approach. And there is no solving of autonomous driving without the right AI approach. So what do we see today? Today, most of the majority of the networks that we have are supervised deep learning networks. You see on the left-hand side. They are trained on labeled data. So all the players in this industry have thousands of data labelers. So our key competitors, you will also not find this in any annual report from them. They have more than 3,000 data labelers in Sri Lanka, low-cost countries. India is the next biggest hub of data labelers. And it's very interesting, there's also now the ethical discussion starting on data labeling and moving them to low-cost countries, etc., and what this means from the labor force. So the AI labor force effects is another interesting side discussion that's also happening, but also an important one. And so most of the players follow this approach, and usually in these networks you have three layers. There's an input layer, a hidden layer, and then the output layer. And you need to fill these networks then with massive amounts of data, with costly data collection, storage, 100,000 of miles that you need to do. You need to label that data. And these networks are usually very rigid. So if you do any changes or feed it with other data, you need to retrain and revalidate those neural networks. And that's why, for example, you also even see with Tesla, when they're now announcing that they have a new neural network approach, they changed from the 1.2 megapixels cameras to 5 megapixel cameras, from hardware 3 to hardware 4. The software stack will first support the current hardware version 3, and only then with a 6 to 9 months delay the hardware version 4. So you see even a player like Tesla that everybody is following, saying they have one central stack, one central solution. Now they are also facing variances for their first time, which I think is very, very interesting to follow what Tesla will now do. And maybe they are becoming like the players that they are actually planning to disrupt. So what do we do differently? So our networks are self-learning networks. They are adaptive, and they really rely on the concept of sparsity. And I will explain about sparsity in a second, but one of the key or core technologies in here and aims is to be as efficient as possible, while being also as adaptive as possible, so that you don't need to retrain the networks. And we basically use a self-learning AI without any labeled images for training to develop these networks. And that reduces the amount of compute that's required. That can reduce the hardware costs on the other side that you need then to run these networks in the car. And at the same time, these networks are very robust and can be hardware sensor agnostic, so very, very flexible networks. And the key underlying technology for that is backed by more than 200 patents from Autobrains and our mother company Cortica. And this is the concept of signatures. So the fundamental AI problem that you usually have is in autonomous driving is the representation problem. So how do you teach a machine what represents the world? And you as humans, you don't use labels or bounding boxes when you learn, right? You don't classify, this is a bicycle, this is a pedestrian, this is a vehicle. This is not how you learned these concepts. So we use unlabeled images, and what we do is on a pixel level, we translate these images into signatures. And you can think of these signatures as binary representations of the image, which is hyperdimensional and very, very sparse representation. And then you will find similarities or similar, let's say, types and strings and parts of these signatures in similar representations and concepts. And you can put them in a large database, and then you will have meaningful concepts of the world. But it's always a representation, and you can give it a name or afterwards and tell the machine that this is a vehicle, this is a pedestrian, but the system has not learned based on predefined classes what it's actually seeing. And so it's much more mimicking like we humans learn, or you learn as children, if you see something in the world. And the real benefit here is that you can do this in a very, very efficient way, because we talked about efficiency today, and this is an approach following efficiency. And why do I say we're trying to mimic what humans are doing? Because this concept is actually inspired by neuroscience. There was a neuroscientist, Horace Barlow, that proposed the efficient coding hypothesis in the 1960s. And that's basically saying that all humans or all mammals try to use as few neurons as possible, or activate as few neurons as possible when they are trying to represent or learn something. So the sensory relays and the code sensory messages, they are reduced in redundancy, but little information is lost. And it's like the Beatles song, sparsity is all you need, that you can think of like that. But of course you have a trade-off, because on the one hand side you want maximum sparsity, so very, very efficient systems and representation, but it needs to be as generalized as possible or as necessary. Right, so this giraffe example here, once you've seen maybe the head of the giraffe, or then you will think, okay, the other part of the body of the giraffe is still the same concept of the giraffe, or when it's now just a teddy giraffe, you will think, okay, this is still a giraffe. But the question then becomes, where do you make the distinction? What is the real giraffe animal, or maybe the teddy giraffe? So that's the concept then of, is this too generalized of a concept, and where do I need to then go back to specificity? But if you follow this approach and these trade-offs, what we achieve is, with this translation into signatures, a more granular representation that's more robust to edge cases and noise and transformations of concepts. So we see in our perception software very good results. For example, if pedestrians are occluded in an images, that it's still recognized as pedestrians. And because you are compressing these representations so strongly, there's really low compute requirements for processing, which leads to lower costs. And a significant amount of less data that we need to train our systems. For validation, of course, is a different topic, but on the training side, it's much less data that we need. And one such example that I want to show you of the self-learning AI is that our R&D team did in Israel is what you see here. We fed the machine or the algorithms different video clips and scenarios from a simulator. We also did it with real driving data, of course. And you see this endless stream of data is then mapped to the signatures, yeah? And it creates this agnostic dictionary of driving scenarios. And you see now the clustering already here on now this happens in hyper-dimensional space. So I just translated this to two-dimensional space for the sake of the presentation. That you see already a few clusters of, for example, overtaking scenarios and overtaking skills, because there's a correlation of these systems or of these clips. Or for example, an autonomous emergency braking skill. So it's only video input and the actuation or decision-making input into the system, and the machine learns and clusters unsupervised in a self-learning way which skills are necessary for which scenario. And this brings me to the third point that is in a heated debate in the AI and self-driving community at the moment, because we see two schools of thought on how to deal with this. And there's, on the one hand side, this approach to say, let's put perception and decision-making, planning all together. This should be one end-to-end network that we train. And Tesla has been now famous to bring their new FSD version 12 to that system. And this yielded the first good results. Of course, if you have millions of video clips to do that, and they are maybe one of the few OEMs that's capable of doing that at the moment. But on the other hand side, you have to also think about yourself, how you learn. Do you have in your brain one model that explains and learns everything? Right? There is not one model for you to learn writing or to learn how to play an instrument. So one generic end-to-end AI system is really too large and has so many degrees of freedom that it's also not you will get immediately to diminishing returns. Yeah. And the other approach, this is a more modular approach that other players are following, is to say, let's keep these two problems separate, that we keep the perception, the planning, and the decision system separate. But from an AI problem-solving perspective, that's also not optimal, because you are not jointly optimizing. Yeah. So the solution that we suggest is to have narrow AI agents that facilitate this long tail or edge of the problem, and these narrow AI agents can then scale. So that could look like the following: that you receive a sensory input into the system. For example, I'm driving in the street and there's a ball coming into the picture and there's a child running behind it, and there is now a perception router, and this perception router is responsible to pick the right brain for this specific situation. So there's many narrow AI agents that are very good at a specific task, and the perception router, based on the sensor input, picks the right brain to complete this task, and to pick the right brain that's the most common or successful at this task, and then to do the decision-making or actuation at that point. And so when you think about this from going from level 2 to level 4 systems, the idea is that maybe today with relatively simple systems, that's a few skills that you need. But then you can cover more and more scenarios, and you don't need to retrain the whole system, because you have specific skills to cover specific scenarios. this is for us a more methodological and modular approach to scale from ADAS to AD. And these skills can be proprietary, they can be open source, they could be developed with an SDK, and can then be the end-to-end solution or narrow optimized solution in perception modules. So these are some of the things that we do at Autobrains. As of today, we are heavily focused on what is commercial in front of us. So that's the ADAS business. There's a lot of money that's burned in level 4 systems, so we set our strategies to focus on ADAS. But I think what makes us different is our core technologies of self-learning AI and signatures, because that's something that, from a technology perspective, can also scale then later to higher levels of automation. And so if you're interested in maybe spending less than 100 billion, then welcome to talk to us and jointly develop, bring ADAS to the streets. Thank you.
Thank you, Manuel.